the lecture. And remember the last, I guess on Saturday, we discussed about the Einstein's field equations, right? And when we discussed about these field equations, we actually discussed about certain conditions that you should have for these field equations. And one of those is actually we should be able to reduce those field equations to the conditions, or we have to show that we can reduce these equations to the Newton's equations at the end. Right? So that is what we are going to discuss here today. And there are a few different ways that you can do this. But for us, so I have chosen a certain way just to show you that how we can reduce these Einstein field equations to the Newton's equations. And this is based on something called Poisson equation that we use for the Newton's theory. Now, when we think about the principle of consistency in general theory of relativity, right? Remember that we talked about principle of consistency. So what we have stated there is we should be able to make the same predictions as the Newtonian gravitation under appropriate non-relativistic conditions, which means once you have this advanced theory, we should be able to apply the relevant conditions that is appropriate for Newtonian gravitation, and we should be able to derive those Newton's equations, right? So that is the idea. Now, so what are those conditions then? Right? So these conditions should be non-relativistic conditions. And there are three basic conditions that we can apply for Newtonian theory. So the number one is particle is moving relatively slowly. So which means you don't need to consider about, high speeds like speeds compared to the speed of light. Right? So what we are considering for the Newtonian theories is the particles are moving relatively slowly, which means the speeds are smaller compared to the speed of light. Right? So everybody knows this. And the next thing is for the Newtonian theories, we assume that the gravitational field is weaker. Right? Remember that we have discussed that Einstein field equations and this Einstein's theory of gravitation is more useful and important when you have strong gravitational fields, which means that close to the sun and close to these massive objects like black holes, those kind of things, right? And because of that, when we talk about Newtonian gravitation, we can assume that our gravitational field is somewhat weaker, right? And the other thing is the field does not change with time. And we call this as a static field, right? Those are the three conditions that we are going to assume to derive Newton's equations from general theory of relativity, right? Now, to start with, now we can show that the divergence of a gravitational field at any point is given by this particular equation. So I guess some of you may have heard about this equation as well. This is the divergence of the gravitational field, grad dot G, right? And that's actually the definition, right? Grad dot G is actually the definition of the divergence. And I don't know whether you have done that when you can actually explain this, what divergence means, right? What divergence means, right? Now, if any of you have any doubts about this, you can just let me know. I can have a separate slide with some diagrams to explain it. But so I am going to take this equation directly. So that is the divergence of the gravitational field can be written in vector G equal minus 4 pi G times rho, where rho is the mass density, and this is for Newtonian gravity, by the way. And we can then tell that the gravitational field G can be written as the gradients of the scalar field phi. So that is G equal minus grad phi. And then you can substitute this G equal minus grad phi into this equation 1, where you can get grad dot phi, which is basically equal to grad squared phi equal 4 pi G rho, right? And this grad squared is what we called as a Laplacian, right? So we call this as the Poisson equation now. Grad squared phi equal 4 pi G rho, and this is based on the Newtonian theory, right? And I assume that you may have seen this equation before at some point. And so our plan is to derive this equation starting from the Einstein's field equation, right? So what we are going to do is to prove the principle of consistency, which means under appropriate conditions, the field equations can be reduced to this particular equation, which is the Poisson equation that we can write for the gravity under Newtonian theory, right? So that is our plan. Now, so once again, the conditions are actually these three conditions. Particle is moving relatively slowly, and the gravitational field is weaker. The field does not change with the time, right? So those are the three conditions that we are going to use. Right. Now, we are going to use those conditions. Now, we normally have this metric tensor G mu nu. Now, under appropriate conditions, which means if the gravitational field is weaker, we can assume that G mu nu can be written as neta mu nu plus H mu nu. And this term neta mu nu is what you get as the Minkowski metric, which is the flat space, right? Now, the flat space, you don't have, any curves that happens due to the gravity. And what happens is we are going to add a small or weak gravitational effects here, which can be depicted from H mu nu, right? So we have the flat space plus a weaker gravitational field, because this is where you can apply the Newtonian theory, right? So I have mentioned here the neta mu nu is a Minkowski metric. So all of you know that Minkowski metric is for the flat space time, right? Where you do not have any curved space due to this gravitational effects, right? And then plus H mu nu is a small perturbation that happens due to the weak gravitational field. So you have the flat space, and then you have a small perturbation for that, which comes due to this weak gravitational field, right? Which is kind of an ideal situation to discuss about the Newtonian gravity. And this value of the H mu nu is, we assume that it's, very pretty much less than 1. So that is the assumption. And then the next one is, we will also assume that the weak gravitational field approximates the energy momentum tensor for dust. And that is the next assumption. And so we assume that remember the energy momentum tensor that we discussed last week. So it has, 4x4 matrix, which had like 16 components. And then we talked that this energy momentum tensor can be reduced to two other special cases where you have dust and a perfect fluid. And when you have a dust, you only have this very first term of the energy momentum tensor, where the rho c squared term. And if you have a perfect fluid, you only have the diagonal term, right? So those are the two, situations we will be discussing most of the time. Now, for this particular situation, we assume that the energy momentum tensor can be represented only for dust, right? Under these three conditions, where you have weak gravitational field, slow speeds, and then the next one is the field is static, right? Not changing. So under these things, remember that you had all these velocity terms for all the other terms except the first one, right? So under these conditions, we will assume that T mu nu is given by rho u mu u nu, and then that is the tensor component, but the actual component is only the first component, where T equal rho c squared, right? So I have it here as well. So we will assume that the weaker gravitational field approximates the energy momentum tensor for dust. So that is T mu nu will be equal to rho times u mu u nu, and then again T equal rho c squared. Right. Now we can substitute this equation 6 and 7 into the Einstein's field equations, right? So when I say Einstein's field equations, there were different versions of that. And remember that the last Saturday, I told you that if you need, you can actually change the Einstein field equation to this format right here. Now let me take that lecture, this lecture file, show you this condition. So right here, remember that I gave you a problem asking that show that the original Einstein field equation can be written in this format, right? So I said that I will include this in your next tutorial, but you can try it yourself. So these are the same equation in two different versions. So what I am going to use for this particular situation is this equation right here, where I have asked you to prove, right? So it says the key tensor R mu nu is equal to minus kappa times T mu nu minus half G mu nu T, right? So that is what I am going to use here. Right. Now, once you substitute rho mu nu into this term right here, and then also T equal rho c squared into this term right here, you get equation 9, right? So I guess all of you are clear with that, right? So R mu nu equal to minus kappa rho u mu u nu minus half G mu nu rho c squared. So once again, what I did was you get this term and that term, where you have these terms by assuming those dust tensor and some of the other assumptions for the weak gravitational field, and then you substitute these two values into the Einstein field equations right here and here, and then you get this equation, equation 9, right? The next step is to substitute the weak gravitational field metric, that is equation 5 into equation 9. So let me go back here. The equation 9 is right here. There you have the field equation, and I substitute the energy momentum tensor and this value of T here to the equation. And now what we have here is this equation, and inside that you can see that there is the metric tensor G mu nu, right? So what I have explained in the previous slide is this G mu nu can be replaced from this equation right here. So where G mu nu equal to neta mu nu plus H mu nu, right? So you can use this now, neta mu nu plus H mu nu instead of G mu nu. So that's what I have done here. So you have everything written in the same way as you see in the equation 9, and apart from that, I have added this term right here and replace G mu nu, which was here, right? Neta mu nu plus H mu nu. So I guess this should be clear for you. And then the other thing is, now for this component right here, where I applied T mu nu, which is equal to rho times U mu U nu, we have to calculate this, right? But the good thing here is what we know is there is only one non-zero component in the T mu nu matrix. So that is T00, right? Because this is written for the conditions where you have dust, which means in the energy momentum tensor, you have only one component. That is the very first component of the tensor, which means in terms of indices, that will be T00, where both nu and mu equal to 0 for that particular component. Now, if both these are 0, then your value will be rho times C square. So therefore, we may focus on only on the R00 term, right? So I guess if I go back again, I think you can understand what I mean here. You have the Ricci tensor here, R mu nu. But what we know here is for the energy momentum tensor, it's represented on the right hand side, you have only T00 component, where the mu and mu both equal to 0, right? Because of that, we can only focus on R00 term here, because both mu and mu will be equal to 0 for that term. So that's what I have mentioned here. Therefore, we will focus on R00 term. And now, if you look at this U mu U nu term, which I have written in the equation, from the definition of 4 velocity, and I assume that you have done this in the special theory of relativity. The U mu term, this is called 4 velocity vector. You have 4 components: U0, U1, U2, and U3, and this is usually written as dx mu over d tau. Tau is like the proper time, and this is also written in this form as well, C gamma and CV. The C gamma means that first term right here. The C times V, this represents the last 4 terms, right? Which are basically 3 components to 3 other directions, velocity components. And this is the time component, C gamma. Now for the Newtonian limits, the advantage that we have is we know that the gamma will be roughly equal to 1, because we are considering low speeds, right? Remember this gamma term, gamma factor is like in a special theory of relativity will be equal to 1 over 1 minus v squared over c squared and the square root of that, right? And that factor will become 1 if we consider non-relativistic speed, right? So that's what I have mentioned here. And this U naught is actually should be not 1, this should be C, right? So there is a small mistake here, we make that correction. So let me make it here. So this should be actually not 1. It should be here. So that U naught should be equal to C, not 1, because that is the first term, the time component. So you will, so I will upload it. Right, so which means you can see that U naught term will be equal to C squared, even though I have written it before, so I mentioned the reason here. And also, when you look at the metric tensor, it is written as G mu nu equal neta mu nu H mu nu. But now we know that we are only considering the 0, 0 term here. So G0, 0 will be equal to neta 0, 0 plus, it's 0, 0. So what is important here is when you write the neta 0, 0 term, that is the very first component of the Minkowski metric, right? And if you remember the Minkowski metric, that very first term is equal to 1, right, which I have not mentioned here. And because of that, if you go into this situation right here, which is what I have mentioned here, the neta 0, 0 component, which is again, just think about the Minkowski metric. For the flat space, you have only diagonal terms. The first one is 1, and all the other diagonal terms are minus 1. So 1, minus 1, minus 1, minus 1. So that's how it is written, right? Now for that, when you are looking at only the 0, 0, 0 term, that is the very first term of the Minkowski metric. And so that will be equal to 1. And apart from that, you have H mu nu term, and regardless of, you can, if you need, you can write like H0, 0, but regardless of what you have here, we have assumed that that particular part is lot less than the value of 1, right? Because of that, you can approximate this term neta 0, 0 plus H mu nu can be approximately equal to 1, right? Which is basically the value of the first component of the Minkowski metric. And this give you a final version for the equation 10, which is right here. You can see that equation 10 is written as minus k rho mu nu, and now this part rho mu nu, this is when you write R0, 0 here, this will become U0, U0. So that is C squared, which I have just shown you a minute ago. And then you get minus kappa times rho C squared. And for here, neta mu nu is what you have as neta 0, 0 plus this small term. And this whole thing will be equal to 1, right? Because this term is equal to 1 when you have R0, 0 term. And that's what I have shown here. We are focusing on R0, 0 term. And because of these two reasons, you get C squared right here. And apart from that, for the metric tensor where you had right here G mu nu, now it is equal to 1, right? And because of that, this G mu nu term, which was equal to neta mu nu plus H mu nu, has disappeared because that value is now equal to 1 when you consider the 0, 0 term, right? So which means finally the answer will be, you just have rho C squared minus half rho C squared inside the brackets, which will give you the final answer as minus kappa half rho C squared, right? Now this is what you get for the Einstein's field equations under these reduced conditions, so where you have a static weak gravitational field, which you have also these speeds pretty much lower compared to the speed of the light. Right? So that is the idea. Right. Now we have one expression from the Einstein's field equations. Now let's look at the Ricci tensor. Right. Now the Ricci tensor is given from this particular equation. If you remember, we have discussed this Ricci tensor before. And what we are interested here is only the 0, 0, 0 term, where you have both zeros for mu and nu. So which means you can take the same expression and plug the value for mu equals 0 for mu, and then nu equals 0 for nu, right? And then rewrite the same expression. So what I have done when I go from equation 14 to 15 is just replace mu's and nu's by zeros here. You can see that I wrote here 0 and 0 instead of mu and nu here. And again, for the mu and nu, I wrote 0 and 0 like that, right? So that's what I have done. Now for the weak gravitational field, we can assume that we are almost in the Minkowski space, and hence the coordinate system is nearly Cartesian. I hope that everyone can understand what I mean here. So we are in a weak gravitational field. If we are in a weak gravitational field, we can, instead of having this metric tensor G mu nu, which we have written here as which is equal to neta mu nu plus H mu nu. Because of a weak gravitational field, this H mu nu is very small compared to the Minkowski metric. Because of that, we can assume that we are almost in the Minkowski space. Right now, if we assume that particular condition, I have a question for you. In this equation, which is equation number 15, what will happen to these 4 terms here for the Ricci tensor, especially what will happen to the last 2 terms. So, you know, for the Ricci tensor, we have 4 terms. The first 2 terms are, you know, just a derivative. We are trying to take the derivatives of Christopher symbols of connection coefficients. And then we have another 2 terms, which are, you know, multiplications of connection coefficients. Now, what we can tell about these 2 connection coefficient terms, the 3rd term and the 4th term of the equation 15? Anybody have an answer for that? If we are in a Cartesian space, and if we assume that roughly that we are in a space where it is very close to the Cartesian space, or where we can replace the Minkowski metric here, what will be the values of connection coefficients? Now, these are like very, very fundamental things that you have to understand, special theory of relativity, right? So if you have the idea that you are, idea, or if you have the basic idea behind what we mean, or what actually we are calculating when you calculate connection coefficients, you should be able to answer that. I mean, if you are in a flat space, what is the value of a connection coefficient? that nobody have an answer for that. If you are in a flat space, what will be the value of the connection coefficient? Now, if nobody can answer for this question, then maybe not easy for us to go from this point to the next steps, right? Because the idea, I mean, it is true that you can't remember the mathematical equation that you need to calculate the connection coefficients. If you need that in an exam, I can give the connection coefficient equation. But what I cannot give in an equation is what it means, right? What kind of thing that you are going to calculate it and why you need connection coefficients. Right? So these are like, basic things that always you should have in the back of your mind when you study a subject like this. Otherwise, no point of learning them. Because these things you should be like, in touch at each and every time, right? When we especially talk about these kind of subjects. Now, why we actually needed connection coefficients initially? Something that we didn't talk before. Now remember that we had to talk about connection coefficients because we are in a curved space, and in a curved space, when you are going to do the differentiations, your unit vectors are not constant to a certain direction, right? So they keep changing. Now, this changing unit vectors you have to represent from the connection coefficients, right? So that's what has happened, because when you do a differentiation, you cannot avoid, telling that these connection coefficients are constant. You can do it for Cartesian coordinates, right? But for this kind of, curved space, we have to use something called curvilinear coordinates. I don't know whether you have talked in this in vector calculus in your first year about the curvilinear coordinates, which the idea is your space is curved, and because of that, these unit vectors keep changing, right? And then you have to differentiate those, and that is why you need these connection coefficients, right? And we come back to this point again then, right? So we can actually assume that these connection coefficients are very small when you talk about weak gravitational fields, right? Because you are going to assume you almost the Minkowski space. Yeah, don't actually need to worry about the connection coefficient. So we assume that those connection coefficients are very small for Minkowski. When you assume the Minkowski space, and because of that, you can straight away remove those last two terms. So that is the idea. And this is one reduction that we are going to do for this equation about calculating the Ricci tensor straight away. Now remember, you should get the idea now. What I am doing here is, as the first step, I took the Einstein field equation, and then applying conditions that are appropriate for a weak gravitational field under Newtonian gravity, I derived an equation for the Ricci tensor. Right? And I am going to do the same thing by directly taking the the Ricci tensor equation. Yeah, the expression we have to calculate the Ricci tensor straight away. And again, I am going to reduce it by applying these conditions that is appropriate, that are appropriate for Newtonian gravity. Right? So you will end up having these two terms, and then when the gravitational field is static, right? Which means when it does not change with the time, then what happens? Now you have two terms. When you approximate, you are almost in the Minkowski space. The last two terms go away from the Ricci tensor components. For the Ricci tensor, remember you have four different components. It's a combination of four components. In the last two terms, where you write the multiplication of different connection coefficients, those two straight away go away when you assume that we are almost in the Minkowski space, right? And the coordinate system is nearly Cartesian, right? The reason is, if the system is Cartesian, we don't need to worry about these connection coefficients. So they should be very, very small even you have a slightly smaller curvature. So that's the idea. So you remove that, and then you have these two terms remaining, where the derivatives of the connection coefficients. So that this tells how the connection coefficients changes with these coordinates. And once you assume this gravitational field is static, then what happens is, what do we mean by like gravitational field is static? So what that means is the gravitational field does not change with the time, right? So it will be a constant with the time. Now when that happens, this term right here, the first term, right? You can see that this is the derivative with respect to x0 term, right? X0 term is quite normally. So that is the time component. And then x alpha is basically represent all the other spatial components, right? If the gravitational field is static, which means it does not change with the time, right? So what that means is this first term right here, where you have the derivative with respect to time component, should go away because the gravitational field is static. It does not change with the time, right? So which means this term should be 0 or approximately 0. And at the end of the day, what you have for the Ricci tensor is only this term right here, the derivative of the connection coefficient with respect to spatial component, right? So make sure that you understand it in that way. And now we have a task here. So we need to look at what is this connection coefficient, rho alpha 0, 0, right? So we have to take that connection coefficient and differentiate with respect to XL. So that is the next task. Right. Now you know the equation for the connection coefficients, even from this equation right here, sigma mu nu. And what we are trying to find here is not sigma mu, that is the connection coefficient, which is gamma alpha 0, 0 term, where you have both mu and nu equal to 0. And because of that, you can substitute mu and nu equal to 0 in this equation right here, and then substitute relevant terms as zeros, which means only the index. So it will be G rho 0 and then 0 rho like that, right? So you will get this equation right here, right? Now you have this equation, and so you have to differentiate three terms here, right? First one is this one. Let's say the second one is this one, and third one is this one. Now, which terms will be equal to 0 here, and which terms will remain in the equation? Now, if the gravitational field is static, Who can answer for this question? If the gravitational field is static once again, so for this connection coefficient equation, gamma alpha 0, 0 is equal to half times G alpha rho, where you have the metric tensor, and inside the brackets you have three terms that you need to differentiate, right? Out of these three terms, so let's say the first one is first term, and the second one is second term, and the third one is third term, then which terms will be equal to, which term will remain out of those three in the equation? So the two of them will be equal to 0, right? In a static gravitational field. Which one is that? So I guess now I have to ask from everyone, right? Because nobody would like to answer. Rangajiva, can you answer for this one? Which term will remain out of these three? I got one answer now. Who else would like to give the answer? Which term will remain? Now, these type of questions you should be able to answer, right? So these are not like $1,000,000 questions, right? So I am kind of giving all the information. I just asked to tell something out of those information. The gravitational field is static, right? So that's the main condition here. And so I have written the equation for the connection coefficients, gamma alpha 0, 0, which has a metric tensor times three other terms, which is clearly written here. So what I am asking is, out of these three terms inside the brackets, let's say first one is the first term, second one is the second term, and the third one is the third term. Which one will remain in the equation? There will be two terms that are equal to 0, and there will be one term that will remain in the equation. Who would like to answer if possible? Navi? So those who are not answering, I have to assume that all of you are sleeping right here still. So I had two answers. So I assume that the Naveen is still sleeping, and maybe, how about Nirmal? Right, so he is not sleeping. Right, so it takes time. So thank you for the answers. It's a third term, right? So it's a straightforward answer. So that's why I asked, because the first one is, when you have these x0 components, first two are, derivatives with respect to time. And thank you, Nimal, Sajini, Acacius, for your answers. And so the first two terms are basically, for a static gravitational field, should be 0, right? Because these are derivatives with respect to time. And we know that this gravitational field does not change with respect to time because we are in a static field. So that is one of the assumptions that we got. So which means we will end up with only having this first equation, right? Half G alpha rho, and then this derivative right here, right? So you have reduced this complex equation up to this point where you can now try to find this derivative only. Let's see what that derivative is. Now for the G00 term, once again, you can write in this way, and we have discussed this before, and this is based from the equation 5. And you can see that G00 equal to eta 00 plus H mu nu, and H mu nu is again H00 term. And when you differentiate with respect to anything, the G00 term, what will happen is this is a constant. So that derivative of that will be 0 because of that, because that is constant. So G00 over dava x, so dava G00 over dava x rho will be equal to dava H00 over dava x rho. Right? So I guess this is clear for you now. And you can see that in this note, I have name all these equations. So that is just to make it easier to refer to the previous equations. There are a large number of equations, right? So that there is nothing special about that. Right now we can substitute. You can see that right. So we have this equation right here, dava H00 dava X rho, which means in equation 19, you have this derivative which you can substitute from this component right now in equation 22, right? Which means your final value for this connection coefficient will be this equation right here, which means now you can write for the key component term in this way. I guess now you should be able to understand it, right? So because previously the key component is this equation 17, right? So all you have is this one right here, and now we know the value of this one. So you plug that right here. So that's what you are doing. So that you will get the key component as like this. So you found this value for gamma alpha 00, and then you plug it here for the Ricci tensor. Right? So this is the expression that you get at the end. And I mean, if you need, you can take, these are constants, right? Half eta alpha rho, because eta alpha rho is one of those components in the Minkowski metric, so that you can take it out. There was actually G, the metric tensor, but you can replace it from the Minkowski metric for the weak gravitational field, right? So that's what I have done here. And then you get dava squared H00, dava x alpha, dava x rho. Now you can use a Laplacian for this one. And right, like here for this expression, you can directly write grad squared H00, right? Now, instead of eta alpha rho here, so I have replaced it from a minus sign. So that is due to the fact that we are using the spatial components of the eta alpha rho only. So you can see that eta alpha rho is basically minus 1 when you only use the three spatial components, right? So that's why we have it here, which means at the end of the day, the Ricci tensor can be written in this form: R00 equal minus half grad squared H naught, right? So this is the final expression that I have for the Ricci tensor. Now remember that from the Einstein's field equation also I had an expression for the Ricci tensor under these reduced conditions for a gravitational field. So we have same expression, like two different expressions for the Ricci tensor from two different methods. The first time we used the Einstein's field equation and these conditions for a weak gravitational field to derive it. Now we have used the Ricci tensor straight away and again use the conditions for the weak gravitational field here to derive this expression. Now we can equate those two if needed. So that's what I have done here. the two expressions for the R0 and 0. So if I go back, you can see. So this is the expression I had from the Einstein's field equation, that is minus kappa half rho c squared for the R0, 0. Now I have this one right here, and that minus half will cancel out because you have that in both sides. So that you can, and then there was also a minus sign. So go back and check it, because the one that I uploaded for you is not a presentation, so it's just a note, right? That has all these equations and maybe extra 1 or 2 equations. So you can write it in this way. Actually, here you don't need detail for rho. I guess that's a mistake. I mean, there will be, once you go through the flow, so if you find that there is something that you feel that should not be here, you can let me know, right? So I will leave that part for you, right? Because otherwise we are not using a board, and I'm not sure the UI when what kind of thing that you can do for here. So make sure that you go through the note. If you feel that, okay, this equation seems to be not correct, just pass me a message in the WhatsApp group, or it's better to have an email just asking that whether this equation 28 is correct or not. Right? So you have the equation number so that I can go back and check it. I guess here you should not have this neat alpha rho, because we assume that it is minus 1, and that minus term goes away when you equate both terms. So what you have is k kappa rho c squared equal grad squared h0, 0. That is what you have by equating the two sides. Now the next question is, in order to go for that Poisson equation for the Newtonian gravity that we derived before, we have to figure out what this h0, 0 is, right? Now this is a different thing. So you have to use the geodesic equation that we discussed, I guess, few weeks ago, which is this equation right here. Using this geodesic equation under these appropriate reductions for the Newtonian gravity, you should be able to show that this gravitational potential phi should be equal to h0, 0 times c squared over 2, right? Now, to save the time, I have not gone through that particular steps here, but you can always refer the book and see what they have done there for that. I mean, it shouldn't be that much hard to understand. And once you get that equation phi equal h0, 0 c squared over 2, then you can take h0, 0 as 2 phi over c squared from this equation and plug that here. So that what you have is k rho c squared, kappa rho c squared equal grad squared 2 phi over c squared. And remember this part where you have to substitute or this relation phi equal h naught naught c squared over 2. I have not derived it here, but I have mentioned what you have to use and how to derive it. So you just use this equation and then apply this appropriate condition, right? Maybe this will also appear in one of your tutorials so that you can make a connection here. But for the time being, you can take the connection here between the scalar, so the gravitational potential phi and h0, 0 from this equation. And then you can take h0, 0 as 2 phi over c squared and plug it here. Right now, when you have the Einstein constant kappa equal 8 phi g over c to the power 4 and plug it here, what will happen is you will end up with this equation grad squared phi equal 4 phi 0. Right? So that is the Poisson equation that we talked at the beginning. Right? So that will complete this proof about reducing the field equations under appropriate conditions so that you can derive the equations for the Newtonian gravity. I mean, you can actually discuss Newton's first law, second law, and all these things in using the field equations, but I'm not going to do all these things because we will not have time. But if anybody is interested, the book has all these things. And so, but for the time being, I just need to give you an idea about this principle of consistency, where you can use the field equations under certain conditions to show the Poisson equation right here. Right, so this is actually what I want to discuss today. And anybody have any questions up here? Right, so if not, let me stop here, and as usual, we will meet again on the next Saturday morning. And I guess we have discussed the background and everything about the field equations now, and we will start talking about black holes and cosmology starting from the next week, and also the Big Bang theory. So those are the three major things that we are going to focus for the next few lectures. How to apply these Einstein equations under different conditions to look at different models of the cosmology, and to understand whether we are in an expanding universe, accelerating universe, those kind of things, right? All that can be done by find the idea is you need to find the correct metric tensor that you have to define the metric for that particular space, and then you solve the Einstein equations and take the solutions, and then you can discuss different things after that. Okay? So that is what will happen for any situation, right? Regardless whether you are using a black hole. For the black hole, then you need to find the correct metric, which is the Schwarzschild metric. We will be discussing about that, and then we will discuss different implications of the Schwarzschild metric, which gives you how the time dilation happens close to a black hole and what gravitational redshift means. And these things, I am assuming that some of you may, in the previous lecture that I did last Thursday for the general degree students, where we briefly discussed what gravitational time dilation means, what gravitational redshift means, right? And what we will do in this for your lectures is we will start from the Schwarzschild metric and derive those things, right? And then the next step will be talk about the Robertson-Walker metric, where you can derive something called Friedmann equations out of that. And these Friedmann equations, we can talk about different modules of the universe, like whether the universe is expanding, accelerating, and density of the universe, those kind of things, right? And these are not that much hard to understand. And at the same time, it's very interesting, right? So make sure that you join and keep up in the lectures. It is easy to get lost easily in these kind of lectures, right? With all these equations. Right, so if you do not have questions, let me stop for here. And as I told